Hello, sir. Dr. Bishwajit Rai, sir. Dr. Bishwajit Rai, sir. Dr. Bishwajit Rai, sir. Dr. M.K. Ilampunan, sir.
I'm here, madam. Or join
Okay, sir. Shall I? Join monitor, sir. But
no, you can start.
okay, sir. Okay, sir. Okay, thank you. Good evening, everyone. I welcome you all to the ATAL sponsored 6 days online faculty development program on recent trends and advancement in integrated power systems. Now I request Ms. S. Divya, Assistant Professor, Department of EEE, Bharat Institute of Higher Education and Research, to introduce our resource person. Now I hand over the session to Ms. S. Divya.
Ma'am, may I audible?
Yes, ma'am. You can start.
Okay. Good evening, everyone. It's an honor and privilege to introduce our distinguished resource person, Dr. Biswajit Rai, Associate Professor in the Department of Electrical and Computer Engineering, Colorado State University, United States. Sir has obtained his bachelor degree in Electrical and Electronics Engineering in 2006 from National Institute of Technology. Sir has completed his MS in Electronic Design and Technology in 2008 from Indian Institute of Science. Sir received his PhD in Electrical and Computer Engineering 2013 from Purdue University. Before joining Colorado State University, Sir was an associate professor at the University of Alabama. Sir worked in SanDisk Corporation, Milpitas, California, developing 3D NAND flash memory technology. Sir has research interests span the boundaries of electronic devices and systems with a particular focus on improving security, reliability, non-volatility, and energy efficiency of solid-state storage systems. Sir published more than 75 research papers in international journals and conferences. Sir hold many patents. Few of them are cell current based bitline voltage system and method for programming a memory device with multiple writes without an intervening erase, system solution for first read issue using time dependent read voltages, apparatus and method for preconditioning current to reduce errors in sensing for non-volatile memory, word line dependent temperature compensation scheme during sensing to counteract cross temperature effect, and temperature dependent sensing scheme to counteract cross temperature threshold voltage distribution winding. Sir has received many awards, among them NSF Career Award, NSF EPSCOR Research Fellowship, and University Distinguished Research and Creative Achievement Award at UIH, and many more. We are truly honored to have Dr. Biswajit Rai sir with us today, and we eagerly look forward to gaining insight from your expertise and experience. I welcome you, sir.
One
Thank
small
you
note
for
to the
the
participants. Yeah, please,
introduction.
sir. Yeah.
Yes. Yeah, please
One
go
small
ahead.
note for the participants. I'll just introduce one more concept. Actually, I'm Dr. Ilampurnan. The thing is, we have the previous session, which was completely the healthcare oriented, and there is a AI based and IoT based device connections and all. And I hope the participants were enthusiastic in that particular session. and the same enthusiasm will continue for this session. Actually, SAR is very well expertised in the backbone of all this AI and IoT. That is the memory-based storage devices, which is actually acting as a cloud storage for all this input from the sensors um, and the storage devices. So participants should make use of this opportunity and ask him the questions so that getting clarified for that and make this session more interactive. Thank you, sir. I will just hand over the session to you, please.
Yeah, thank you. Thank you for making the connection, and thank you for everyone joining, and thank you, Professor Dibya, for introducing me. It was a very long introduction, but anyway, so can you see my slides? I mean, my first slide is shared. Please give me some
Yes, sir.
feedback because it's
Yes,
an
sir. Yes,
online
sir.
mode. Yeah, so I will keep going on, but I will not realize. Let's see.
Yeah. Make it in a presentation mode. Yeah, a bit better.
Yes, so
Thank
this
you.
should be the presentation mode, and if there is any glitches in terms of listening my voice or some slides, so please, I mean, unmute yourself and let me know, because otherwise I will not be aware that I'm not with audible. Okay, so I think some of you, either Professor Dibya or Professor Rajalakshmi, please, I mean, let me know that I'm audible, my slides are visible, and everything is going okay. So I know it is 1.5 hour talk, so I prepared accordingly. Maybe
Yes.
we'll go on up to 1 hour. So, and then we will have some question answer session in between. Also, I'll give a pause and I will see if there is any question in between. Yeah, first of all, I mean, for me, it is early morning, 7 a.m. So for me, it is morning, but I know it is evening for you. So good evening to all. And I know you will have dinner, and also I'll not hold you long. So, but I think I'll get started. Okay. So my research is mostly on the reliability and security side of microelectronics. And that's why I named my lab as RAM lab, because one is RAM is one kind of memory, and also the university I am in, their mascot is a RAM. So that's why I thought to give a name of my lab appropriate. So that's the origin of RAM lab. And with that, let me go ahead and a little bit about my background. I mean, it has been already detailed earlier, so I just want to tell you what I did in all those educational institutes. For example, during my PhD at Purdue, I worked on solar cell, or more specifically, solar cell reliability. And then I moved to SanDisk after my PhD, working there almost 5 years and working on various types of flash or non-volatile memory products development. And then I came back to academia, and here I utilize my expertise both from PhD as well as from my industry experience in order to solve problems related to security or, say, harsh environment reliability. So that's my background or experiences. And in today's talk, I would like to give it in two part. I know here we are talking about um, power systems or a connected power system. So here, security is also a big part of any connected system, right? So I will talk the fundamental aspects of security. What are the recent trends, and what are the most challenging issues in security? That will be the part A. I'll spend almost say half an hour on this. And part B, I'll talk about on reliability of photovoltaics, so which is my PhD topic. So I thought for this audience, both security and reliability will be interesting. So that's how I designed my talk. And after each and every topic, I will pause to see if you have any questions. I'll be happy if you have any questions, because that's how I'll know that I'm making more sense. Otherwise, it is just one-way traffic. So, so yeah, please stop me anytime, or when I give a pause. Don't be shy to ask questions. Okay, so with that, let's get started with my part one, or part A, which is the security of the connected world. So we live in a connected world where everything, starting from our health, from our car, from anything from our home, everything is connected through internet, right? And definitely the power system is also connected through internet. Someone can control remotely many of those settings, many of those functionality. Now, one important aspect of of this connected world is there are billions of devices. Billions means, since numbers are high, these devices has to be resource limited or low cost, right? So many of those, think about our fitness belt or Fitbit, or say many other smart watches. These are very tiny device, and these are resource limited, right? The hardware inside is very small and less powerful, but they are generating very valuable data, right? It can be your financial information, it can be your health information. So this should not be hacked. And that's why the challenge is, because if you have a very powerful computer, you can store your data more securely, right? And but here we are talking about a tiny device, and still we want to ensure security and privacy. So that's the challenge, that in this connected world, that there are billions of devices, and most of them are resource limited, and still we want to ensure the security and reliability. And there are several challenges in this connected world. So here I list out some of them, because I mean, we call it edge. Edge is more like in the, not in the data center. Data center is a centralized. The edge is like at the user end. So when the devices are designed at the user end, these are the five challenges, very important. One is they run on a limited power. So think about your smart watch. So that runs on a limited battery power. So it has to be energy efficient. It has to be low cost, because we are talking about billions of these devices. And then they have to be reliable, they have to be secure, and data has to be private, right? So these are the all challenges that maybe can be ensured in a centralized big data center or centralized computing facility. But it is very hard to do it at the edge, where the devices are resource limited. So that's the big motivation for working in this area, that how to make sure, even though device is resource limited, how to ensure its security. And this talk, I'll talk about some of those issues as well as some of those possible solutions. Okay, so one big issue right now in the in this world is this counterfeit electronics. Right, counterfeit electronics is a very broad term, but the origin of this issue, which was not there, say, 10, 20 years ago, right? So think about 20 years ago, we never talked about much on counterfeit electronics. It's a very recent issue. In last 10 years, it has got as a lot of attention, mainly because of the electronic waste are increasing, right? So every one of us, we use smartphone, smart devices, and we throw them out in 3, 4 years and buy new one. So where those discarded electronics goes, right? What are the issues with those discarded electronics? So this is just for illustration that how counterfeit or not genuine electronics comes back into the supply chain, right? For example, you throw them out, then the PCBs from many of those devices can be taken off, can be scraped off, and then in the PCB there will be a lot of ICs left. So even though your entire system maybe become non-functional or not usable, but the ICs there many times still remain functional. So, so that there can be a motivation to bring them up and then recycle them and sell them as new, which is not legitimate, but that's happens very frequently due to this rise of e-waste, right? Or the way we are using consumer things. Um, we are throwing them out, or we are not we are discarding them very soon, right? So that's why these counterfeit issues in the form of say recycled electronics are coming in. And think about if some of those recycled parts are used in a critical system, like say integrated grid, smart grid application, then it will fail sooner because yes, it is functional during the time it is recycled, but its life is used up, right? So it will not live long. Any electronics has a finite life. So this will basically jeopardize the reliability of a critical application. So how to detect counterfeit parts and how to prevent proliferation of this counterfeit electronics is a big issue, and it will impact in our day-to-day life in many ways, right? So that's the bottom line of this issue, the counterfeit electronics, because we are using more and more devices, more and more gadgets, electronic gadgets, for a very small amount of time, and we discard them many times in the exchange of a better device. So those discarded electronics needs to be discarded in a more safe way, but it is not done properly, and that's where this issue comes in. Now, recycle is just one part of counterfeit electronics. Counterfeit can be several different types. Here I'm listing like remarked. Remark means rebranding. So for example, you can rebrand an inferior device with a superior brand, right? So this can be called remarked issue. Then overproduced, out of spec, these are fab issues. So in the fab, never you get 100% yield. When you say design, say 1,000 chips, always maybe 100 chips will be faulty. So they should not come back into the supply chain, or they should not come back in the consumer space, right? So now, because of different rogue employees or counterfeiters inside the fab, some of those discarded or fallout chips can also come into the supply chain or in the market. So this is another types of counterfeit. Then cloned, forged, tampered. So these are other types of counterfeit that as a resourceful counterfeiter can reverse engineer your device, and they can make a cloned inferior parts, or they can temper the parts, right? They can change some properties of the device. So this paper that I list here list all those issues of counterfeit. So just to summarize, so recycle means used and aged. That means um, its life is less, so it will fail very soon. Remark is rebranding. Overproduced means fabrication issue in the fab. Out of spec means those non-yielding die or fallout material still coming back in the market. Cloning is more like reverse engineering and producing the same part but with inferior quality. And fake and tempered. So these are other issues of counterfeiting. So since I spent a lot of time in semiconductor industry, I know how much goes to make sure reliability of the parts that they ship. So all the chips are tested. So there is a lot of effort goes on. I'll say more than 85% effort is testing and reliability. So if you make something clone and you sell it at the same price, which is not justified, right? Because cloning just not mean that it will be reliable and other things. So that's why these are all issues in the supply chain. So far, am I doing good? I mean, I just want to get a quick feedback because uh, I just want to know if someone can unmute and say, okay, I'm going good, I'll be happy.
Yes, sir, please proceed.
Okay, thank you. Okay. So now, why this counterfeiting is a big issue in this globalized um, market? Because the chips are not fabricated by one company. So this is called vertically integrated supply chain or vertically integrated company, where one company can design, which is sometimes called RTL synthesis, is more like a design, the innovative part. And then you do gate level design, then you make the schematic and um, send it to a foundry, and the foundry will fabricate that chip, and then this die, the wafer, will go for die sorting and packaging to another country. So there are several countries are involved before you get the final product or final end product in electronics, which is the chips, right? Finally you get the chips. So because there are multiple companies are involved, because there are multiple countries are involved, your chips or IPs are
flowing all over the world. And that's why there is a vulnerability of fragmentation in the supply chain. And there can be counterfeiters sitting in any of those countries, in any of those companies. And that's why the problem is global and it is not easy to solve. Had it been a vertically integrated supply chain, where one company controls everything and design is done in one place, this issue would not be that severe. But nowadays, most of the companies are fabless. They don't have fab. For example, AMD is a fabless. So they just make the first two part of the design, and then the fabrication will take place by another company, mostly say TSMC in Taiwan, and then the packaging and final wiring and all will take place in another country. So this is the main challenge, and as you can see, the different in terms of market shares, Taiwan leads in the semiconductor fabrication, and there are many other companies are also involved. Now, because of this globalization, counterfeiting or counterfeit parts are very much prevalent in the supply chain. This is a report from Semiconductor Industry Association. They're saying 15%, right? This is a big chunk of defense semiconductors in US are counterfeit, and they're causing $7.5 billion of loss every year because counterfeit parts are inferior and they will cause they need to be replaced sooner or later, right? Think about you are buying some say thumb drive, right, or flash drive from Amazon. How do you know it is really 1 terabyte, not 1 gigabyte or something like that, right? So this is very hard to tell that the parts that you are buying, are they really genuine or not. So this is just to tell you, this is a big issue right now in the semiconductor industry. Now, this is just one example of supply chain. And so think about, so I come from flash, so that's why I'm giving this example of flash supply chain. So there are very few manufacturer who makes chips, like say Micron, Samsung, Toshiba, and then it goes to different distributors. First, it will go for packaging, and then it will go to the different distributors, which will sell those chips to different system integrators. So system integrators can be very different companies, which will make say end products like SSDs, and also they will then sell the final product to the customer. Now, counterfeiters can sit in any of those places, can be inside the fab, can be one of the distributor who are collecting recycled parts, or can be system integrators and all. So that's a big long chain. Several companies and several places are involved, and this is just to tell you that bad actors, right, which are the counterfeiters, can be anywhere, and finally the consumers would be affected because of the inferior products. And these are few news. You just search in Google, you'll find there are several news where many companies that does not know that they are sending counterfeit SSDs. Because suppose a distributor is the counterfeiter, right? Or some distributors has counterfeiters. Then system integrator will not know, right? They will think they are selling the right product or genuine product, but their parts are faulty. So this can happen, and there are a lot of news on those that people find that USB drives are not not genuine and all. Okay, so now why this detection is so hard, right? So why the system integrator, when they're buying chips, why they cannot ensure that they are really genuine parts or not? The reason is the the semiconductor life cycle, right? This is a very famous bathtub curve, we say it. So whenever we produce any electronics chips or any electronic parts for say, there can be some initial fallout, which call infant mortality, right? At the very beginning in the foundry itself, some of the chips will be faulty, so we should discard them. Now, remaining chips will be good and we should use them, but counterfeit, say, recycled part, right, can occur at the middle of this bathtub, which is very hard to detect because the chips are functional. So how do you know that how much life is left, and how do you know it is not genuine, or it is not fresh coming out from the fab? Very hard to say, but it will fail soon for sure because this bathtub curve is very fundamental with any electronic IC or chips. The other reason is the process variation. So semiconductor fabrication always involve variability. There is no two chips will be identical. So there will be always a variation, and a fresh device, even though say 100 chips coming out from the same fab, there will be a lot of variation between them. So this variability makes also the detection difficult, because think about a recycled part will also be variable, and some properties will be different, but there can be some overlap with the fresh part. So the overlap makes it hard to say, is it really recycled or is it really counterfeit parts or not. So the process variation makes it also difficult. And finally, the high amount of usage. Yes, if you do very high usage, then maybe you can detect, but most of the time the counterfeit will be before it is end of life, right? So that's why it is hard to detect. So chip to chip process variation is another challenge. So these are the technical challenge. Why, say, as an engineer, we cannot detect counterfeit parts so easily. Now, in this regime, so I just don't want to go in much more detail, but the kind of work that I did in say last 7, 8 years is developing an electronic board, as I'm showing it here. We call it evaluation board, where you can plug in any kind of memory chips, and we can tell is it really counterfeit or genuine, right? So even though those technical challenges are there, with some innovative ideas, we can overcome some of those challenges. And these are few papers or few code name of those words. I mean, if you just search with those names, you will find those papers. And if any of you are interested to know more, I'll be more than happy to send those published papers. These are mostly IEEE paper, so I'll be happy to share more detail. But just to give you a brief idea that how we are solving this counterfeit issue. So one is this physical unclonable function, or PUF, which is a very uh, good security primitive, these days very well known security primitive, which is more like a fingerprint. Like, so every human being has a fingerprint. Like your fingerprint, my fingerprint will be very different, and we can identify a person with his or her fingerprint. So every chip should also have a fingerprint, and that fingerprint originates from its process variation. So whenever you make a chip, not all the transistors inside the chips will be same. So by identifying those cell to cell or transistor to transistor variability, we can design a digital fingerprint of the chip. So that's how we can say or give a unique ID of the chip that manufacturer can store. So this is one idea, PUF, or physical unclonable function, or more simply, you can say fingerprint. The other idea we came up with is called odometer, or you can think about in a car, right? How much mileage or how much kilometers the car has gone. We denote it with odometer, right? Odometer keeps track of it. So it is also more like an odometer for a chip. So, and this is designed by counting the defects, because any semiconductor will have silicon dioxide, this kind of insulator. So those insulators store defects over time. And by measuring those defects in an intelligent way, we can tell how long this device has been in use. So we can exactly tell, has it been used for 5 years, or so how many times. So this is the paper where we discuss some of those aspects. And then the third technique we came up with is called watermark. So watermark is more like storing something which nobody can tamper with. So it's more like a tamper-proof storage, right? So for example, whatever you store in, say, your thumb drive can be erased, but in a thumb drive, if you can make some part non-erasable, so that nobody, even with physical access, can change it. So that is called watermark. So it is more for tamper-proof ID storage and all. So all those techniques, right, so are used to solve one of those counterfeiting issue, right? I mentioned at the beginning that counterfeit is a broad issue. It is not just recycled part. There can be several other issues in the counterfeit. So each of this technique cannot solve all those issues, but maybe one of those issues. So that's why there are so many techniques we proposed. And finally, the DNA. So DNA is very interesting security primitives that we proposed for memory chips. So DNA and fingerprint, right? We identify a human being by fingerprint. Like my fingerprint and my father's fingerprint will be very different, but our DNA will be very same. So DNA is more like identifying a family of chips. It can be a technology node, or it can be identifying a foundry or identifying a particular company. Is it really coming from say, Toshiba or some other company? So this is the purpose of DNA, that every chip or every family of chips should have a DNA that is unique for all the chips coming out from the chip. So for all the chips, it should be the same variation as I'm showing here in this little cartoon. Chip 1, chip 2, chip 3 has same variation. But if you choose any other company or any other technology node, that signature will be very different. So these are the few techniques through which you can identify a chip is genuine or not. Now, all these things will also affect in any system integrator or any system development where several electronic parts will be used, right? Think about in a smart power grid. There will be a lot of electronics involved. It can be inverter, it can be power electronics. So some of those ideas can also be borrowed or can also be utilized in an to solve that specific issue for that power grid or something other application. Okay, so I think I will give a brief pause here and want to see if there is any question so far and before I move forward. Okay, so if there is no questions, so I will just move forward. So this is just one part of my talk, this counterfeit electronics.
Vishwadit, that
Yes,
the
yes.
aging sensor, what is the meaning of aging sensor?
So aging means how many times you have used or let's say turned on and off your device, right? So in a memory, say how many times you have write and you have removed your data. So that is the usage. How much you have used this device. So that is the age of the device, right? So now
Yeah.
how to detect
Okay.
that age is through defects in their structure. Yeah, so
Okay.
it's just a name, just aging is a
No, no,
generic
just I
name.
was
Yeah, 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 yeah.
just after seeing name only I was asking.
Yes, yes, yeah. So
Okay.
this is very popular in semiconductor industry. They call it
Okay.
aging effects or aging. Yeah.
Okay. Okay.
Okay. Okay, good. So let me move to the next topic, which is in the part A. We finished just one topic, counterfeit, and I'll go to the sanitization issues. Right? Sanitize. We always after COVID, we always say sanitize your hands, but sanitization of discarded electronics is also a very important issue. And what do I mean by sanitization? Let me explain a little bit further. So sanitization, right, of say SSDs is a very big issue. So there are a lot of reports, and if you can search in Google, you'll see that the consumer they sell sometimes their used SSDs, thinking that they have wiped out all data, they have deleted all files, there is nothing. But once you sell it, once a hacker gets physical access to that SSD, they can recover all your previous data. So that's a huge privacy theft because in SSDs and SD cards, which store a lot of sensitive information, right? It can be financial document, it can be our personal data. So that's a huge issue. And that's why a proper sanitization is important. Think about you are giving away your smartphone, right? Every 4 or 5 years in the exchange of getting a better smartphone, a newer version of smartphone. And you may think that, okay, I have deleted all my passwords, all my photos and files, but it is not. So if someone does not sanitize your device, right? If they don't follow certain protocols, it is very hard to really remove all the traces of previous information. So that's the problem, sanitization problem. And for SSDs, it is even more because in SSDs we store terabytes of data. And not only as a person in a data center, also they store a lot of data, right? It can be financial information, the cloud storage that we all we many times talk about cloud storage, right? Where all those financial information goes or sensitive information goes, they're at the end are stored in an SSD or solid state drive. So that's why many times the cloud storage provider, they mechanically crush, they literally crush those chips. It is definitely not a good solution because it takes a lot of energy to crush and destroy all those chips, and because they knows the sanitization of those used SSDs are not easy. Okay, so that's the problem statement. That is there any el electrical way I can sanitize? Or as a user, okay, as a user, when I'm sending out my smartphone, what should I do so that nobody, even a smartest hacker in this world, cannot recover the data, right? So that's the goal um, of this research. So I will explain this in terms of memory because that's where I did work, sanitization work. So think about if you look at an SSD, if you break it apart, you'll see two different types of chips. One is the square chip, which is the controller chips, and there will be memory chips, which are the rectangular shape. Now, internally, these memory chips hold data, and they are basically transistor device, and little different than usual transistor. It's called floating gate transistor. So the way your thumb drive or your SSD stores information is storage in the floating gate. So if there is no charge on the floating gate, as I'm showing, it's just like say factory out, right? So in after fabrication in a fab, you got all your device which will look like this. They're called erased state. They're in the erased position, and we call them one. And the moment you store charge on them, which is called programming or writing on the device, then it is in the program state, or it will represent 0. So that's how you store information, zeros and ones, or in the form of charge. If there is charge on the floating gate, we say it is 0 because the transistor will be off because it is at a high threshold voltage. And when there is no charge like this, the transistor will be on because it is at a less threshold voltage because there is no charge stored. So that's the way you can store, or all your SSDs or thumb drives store information, right, in the form of charge. So that's the only background you need to follow to say whatever I'm going to say in the next few slides. But one thing is, programming is easy, but once you program, draining out those electrons is very hard. And since SSDs comes with terabytes, so generally they don't, whenever you are deleting some file, right, you are not actually deleting them. You are just overwriting on a new place, or you are just physically or in a logically you are saying those files are not accessible. But in your real chip, those data is still there, because erase means like formatting a drive, right? How many times we format the entire drive or entire your thumb drive? Very less. So that's why the data is still there, but as a software interface, we are not able to access those files. So that's why as a user, we may think data is deleted, but they are really not. Okay, so now programming is easy, so we can program, and that's why the usual way of deleting data is over programming. So I'll give you an example. So let's assume you have written an image, black and white image of an Einstein, as I'm showing here. So the black, which is I think 0, are represented with this red distribution, white. So every pixel in this image. So this is a real image that we wrote in the SSD, and then this is the analog representation that how these threshold voltages will look like. Now, instead of waiting for years, we just baked it to accelerate the wait time, and 3 hours bake, the Einstein image remains the same. But one thing for flash is very important is to know is there is some charge leakage. Yes, you are storing electrons on the floating gate, but some of those electrons can leak out over time, and that will make weaker zeros, right? So the threshold voltage is drifting down, as you can see with these blue and red lines. So after a few years, your blue distribution was just sort of program. It will become like a red distribution after a few years. But yeah, digitally it will be the same, because digitally 0 and 1 remains same. Then you say erase the data, which is means you are programming everything, because programming is easy. So the usual way of quick deletion, right? Or the most state-of-the-art way of deletion is making everything zero or programming all the bits. But here is a problem. So when you program, you're creating strong zero, but new zeros, right? So there will be a difference between an old zero, which is the original zero, and new zero, which is actually one. So after deletion, yes, data will become completely black, and you may think that, okay, the drive is sanitized. So this is the most sophisticated way of sanitization, what I'm talking right now, that making everything zero. Many of those devices even don't do that. But here is the most sophisticated sanitization. And we say that, okay, we can still recover the data because we can see in the analog world, there is a difference between weak zero and strong zero. And if we can know who are weak zero, we can identify which is the original zero and strong zero means original one. And that's what we did. We just shifted the reference voltage because the chip allows to shifting the reference voltage and again read the memory, and we can see the traces of the instant image. Yes, we cannot recover the entire image, um, but we can partially recover them. These are all done on a real hardware, real memory chips from commercial off-the-shelf chips. That means any hacker can do it on your drives as well. So this work has been published, and we got NSF funding for making a more secure sanitization scheme. Okay, so that's one of our work on sanitization. And sanitization issue is not just for non-volatile memory; it is also an issue for volatile memory. So in a computer memory, you may have seen we always look for how much RAM you have. These are mostly volatile because they are faster memory. Volatile means the moment you turn off your computer, all those data is gone. So you may think that, okay, there is no need for sanitization because I turn off power, data is gone. So why I do need sanitization, right? But we found that you still need sanitization even for volatile memory like SRAM, right? For non-volatile memory, we understand is non-volatile, so we need to be sanitized before we discard. But even for volatile memory, our research shows that we need sanitization. And the reason is, so if you look at an SRAM, it is a back-to-back inverter. And there's a very interesting property of an SRAM, which is its power up state. So for example, yeah, so SRAM is very ubiquitous in any electronic parts. It can be think about any electronic parts. SRAM will be a part of it. Think about your inverter that are using in a power grid. As I'm not talking about that power inverter, right? Power electronic inverter. So they are also controlled through some electronics. Some passwords will be stored, and it will be invariably come to SRAM. So if somebody can know your password of this power grid, they can hack your system, right? So that's the problem. So now let's see why sanitization is important for SRAM. Because when you turn on an SRAM, right, it can go to any of the state. So you have not written any data on the SRAM. You just powered it up. Because it is a digital memory, it should go either to 0 or it can go to 1. It has no other choice. Okay, so this is called power up state. The moment you turn on your SRAM device, you don't know where it will go. Will the starting point will be 0 or 1? And this is called garbage value. We call it uninitialized SRAM state or garbage value. So typically process variation determines whether an SRAM cell will go to 0 state or 1 state, right? So because it is undeterministic. And that's why this can be used as a fingerprint as well. So every SRAM will have a very different fingerprint or very different uninitialized state. So this can be used as a security primitive, right? So which is a device specific key or device specific digital ID. But the same thing can be used to recover the data because we found this fingerprint is not robust. If you use an SRAM for long enough time, you can change this fingerprint by the stored data. And that's where the vulnerability or need for sanitization comes. So let me show you how we did our experiment. So all this work that I'm showing so far is are all on commercial off-the-shelf chips. For example, we buy SRAM chips, we put them in a socket, we connect them with Arduino and interface with the computer. So that's how we do our research in the group. And if you are interested in some of those code or you want to know for your courses, if you want to do it in your courses, this is the link. I'll share the slides after this presentation. You can get this link, and you can download the code, and you can repeat some of those experiments if you like. So that's what I'd like to say. So this is our experimental setup, and what we are doing is the Arduino Duo is the controller. It has a lot of pins. So we're connecting all those memory chips pins, right? So that's why the socket means we can connect those pins very easily. Socket is nothing but putting these chips and enlarging those pins basically. And every memory chips has address pin, data pin, and command pin, right? So you have to send address, and you want to get the data out of the chip, and you can say, I want to read, I want to write, I want to erase. These are the control command or control pins. So that's how we interface the chip. And the way we do this power up experiment, or the SRAM uninitialized state, so we just read the SRAM addresses without writing on them. So when you read, you get a garbage value like this. This is the image representation of garbage value. So it's a very random signature. And then what I did is we wrote an image, say instant image, on that memory, and then we baked it. So baking is again like a accelerated aging or accelerated time acceleration. So suppose we bake for say 1 hour, and then we turn off the device. So bake was done in a power on condition. That means it was holding the instant image. And then we turn it off. So presumably data should be gone, right? Because it is a volatile memory. So data is gone the moment I turn it off, but we turn it on again. And when you turn it on again, it was not going to this initial random state. It is going to some traces of Einstein. So that is the experiment we did. And this clearly says that after using an SRAM for long enough time, if you discard it, it will remember what data it was holding. So that is a big issue, and how to sanitize is a open challenge. So that's the thing, and this is more elaborate way to explaining these results. That 10 hours, 30 hours, you can see some shade of Einstein, and 50 hours, we can see almost entire image emerging in the power up state. So power up state is a random state, but it can hold or it can remember the data um, based on the aging signature of it. So this work is still under review, but we got very good feedback, and it will be published, I think, very soon. So I can share some of those results with you anytime you are interested in. Okay, so baking is the issue, and baking means you are changing some properties. The process variation, initial process variation, you are changing by the baking or aging properties of the chips. Okay, so I'll give again a little brief pause because I'm moving to another topic. If there is no more questions, if there is any questions, you can ask me. Otherwise, I'll move to the next topic. Okay, so let me.
No, one thing
Yes.
actually. So when you are
Mhm.
formatting, it's a complete deletion, right?
Yes, formatting is complete deletion. So this is not for SRAM, but for flash. Yes.
Okay, okay.
Yeah, for flash drive,
Fine.
we many times ask for formatting. So
Yes,
that time
yes.
it is real deletion, but we hardly format, right? Many times we shift delete,
Actually, you
we
will
do all
only
those.
for pen drive. That pen drive only will format, but hard disk and all will not format. Nah. Yes.
Yeah, but they can do it.
Yeah.
Manufacturer can offer some functions to format and all, but those
Okay.
are very less frequently used function. Many times when we say delete a file, we are just making it disappear in the software interface, but in the hardware, in the chip, the data is still lying.
Okay.
Yeah. Okay, so let me go to the last part of part A, which is the fault injection attack, and it will be quickly done. So fault injection or intentionally tampering a chip, right? That is another kind of vulnerability in today's world, and there are many ways you can inject fault. You can put a chip in a freezer so that a volatile chip becomes non-volatile, because it is a charge RC time delay, right? Resistance, capacitance, time delay, any chip. So the moment you put in a cold chamber, the RC time constant will be large, and chip will not be losing data so fast. That is one kind of attack people have done. Some voltage based attack that you power it up at a higher voltage, then you physically inject fault, like say laser pulse. You put shine laser and then change the data inside. For example, think about like this. So you have a key password, right, stored in some of your memory, non-volatile, presumably non-volatile memory, and you shine laser, and by shining laser you can make every bit one, because laser pulse will change 0 to 1 and 1 will remain unchanged. So that's how we can make a key, random key, to a known key, which is all one, and that's how you get an access to a system. So these are there are a lot of papers in this area, fault injection attack. Um, so my research in this case is to C, radiation-based fault injection. So radiation is like X-rays. We do many times X-rays for imaging, but X-rays can penetrate through the packaging material, the black packaging material of a chip, and it can really go and deep and change the properties of the cell. For example, I talked about a flash cells, which is storing data in the form of charge. The moment it goes through radiations and like say X-rays, those charge are knocked off, and a programs are like logic 0 will become logic 1, right? So that's a significant vulnerability for any non-volatile memory, and non-volatile memory as the one which are holding passwords and other sensitive information. So that's what this is a significant problem, and there is a lot of work going on how to make it is resistant to this kind of fault injection and all. So I'll not go much detail. I'll just summarize some of my contribution in this area. So first, we characterized many of those flash memory cell in terms of their threshold voltage distribution. So this is a measured threshold voltage distribution from commercial chips as a function of radiation. So radiation, think about space radiation, like ISRO, for example, will be very much interested in some of those data because they have to send satellites. But you can use the same thing for even security vulnerability, because X-ray machines are very common these days, right? If you go to a dentist, they have X-ray machine. So you can put your chips and make all the bits all one, because any radiation will knock out those charge. Then 3D NAND is more like a recent trend in flash industry, that how it is like a vertical buildings, multi-storied building, right? So in order to improve the density of memory, you are getting more and more floors of the building. So these days, 232 layers are available in the market. Most likely, if you buy your next SSD or next thumb drive, they are coming from 3D NAND, and 3D NAND is the technology I worked also during my industry experience. So we've characterized 3D NAND under radiation, that how different layers behave and all. So yeah, so these are the papers which is there. And finally, we came up with a very interesting idea that a flash chips can be used as a sensor, as a radiation sensor. Think about your smartphone, it has a SD card slot. And now SD card is your sensor, because anytime you go through airport X-ray scan or any amount of radiation, a bits will be flipped. And by knowing how many bits got flipped, you know how much radiation you have gone through, right? You can write a simple app in your smartphone which will read this SD card and periodically will inform you how much radiation you have gone through. So these are mostly funded through National Science Foundation here in US, and these works are still, some of these works are ongoing. If you have any interest, any um, curiosity in some of those work, I can send my publication, or also I can share some data if you want to work, or if you want to define a projects for your students and all. I'll be more than happy to share some of those data as well. Okay, so with that, I don't have much time left. I guess I have half an hour left. Uh, so I'll move now to the next part if there is no more question here. Okay. So I'll completely now change my gear or change my topic, because so far I was talking mostly from security point of view of for electronics. Now we'll talk reliability of photovoltaics. And for two reasons, I chose this. These days, I don't talk much about photovoltaics because I moved my research more in the security. But I did my PhD and a lot of um, good memories I have on working with photovoltaic. This is also my very favorite topics, that how to make world sustainable or how to increase the number of application of photovoltaics. Right now, we always think about photovoltaics means our rooftop PV or maybe just the power plant, photovoltaics power plant. But we can be very innovative in terms of newer application for photovoltaics. Think about your car roof, right? These days, electric cars are so prevalent. So electric car is a DC machine, and you can have photovoltaics which your output is DC. So rooftop PV can be a very innovative application if you can increase its efficiency and make it work like that, right? There are other application I saw. The road can be PV because roads are always under sun, but we never use any photovoltaic cells on the road itself, on the road surface, right? I'm talking about large road, and that can power up your city, but we never use that part for photovoltaics. So this is just some of my thoughts. But PV, even though it is little costlier right now, but it's much more integrated now in our power system, day-to-day system. So, and the students always get excited with PV. That's what I find. So I teach a course. I used to teach a course in my previous university on photovoltaics. And I used to find the students, undergraduate students, are very excited. And defining project is also very easy because the small photovoltaic panels I used to give them. I used to tell them characterize these for partial shading. With partial shading of a photovoltaics panel is a very interesting problem. And I used to give this kind of projects to some of my students in that course. But yeah, today's I will briefly talk some of my PhD work, and yeah, then I'll conclude my talk. Okay, so I hope this will be relevant to some of you who are very much involved in energy and renewable energy and other research. So I thought this will give some diversity in this talk as well. Okay, so let me get started with OPV, which is the organic photovoltaics, and its reliability. Okay, so now if you look at the solar cell in general, there are several materials involved and several types of solar cells are available. They are called single junction. For example, you can say high efficiency cells like crystalline silicon, C silicon, 3,5 material, and heat cell or heterojunction solar cell. So these are high efficiency solar cell. And because the material is crystalline, right? Crystalline means it requires very high temperature processing. And that's why the energy cost to produce them is also very high. Yes, efficiency is high, but they are also costly because you need to process them at a very high temperature, right? And that will cause cost, both in terms of energy and price. And then the mid category cells like cadmium telluride, CIGS, micro crystalline silicon solar cell. This will be in the 15-20% range. And similarly, their energy cost is also a little bit lower. And then OPP is the lowest one. The efficiency is low. So this slide, I'm sorry, it's a little old, but I think OPP, I think nowadays exceeds more than 10%. Organic photovoltaics more than 10% efficient. And the energy cost is also very low because most of the time they are processed in a solution environment. These are like ink. You have two kinds of ink, you mix them together and make a thin film. So that's the OPV. And yeah, it is low cost because temperature involved will be around 150 degrees centigrade for annealing and making the film and solution processing. It is lightweight, low cost, and many other applications possible because these are transparent, built on plastic. Think about a paint. Paint, I mean, I saw this kind of building in California when I was working. Their window paint is nothing but an organic solar cell. So the light will go in because these are high band gap material. So light will pass through in, but some part of the light will be converted to electricity as well. It can be used on your jacket, on your laptop bag and all, because they're flexible material. So these are various application space, and that's what I like. I feel like we are missing the trick right now, just thinking, oh, photovoltaics means it has to be on our rooftop or it has to be on a power plant. I think photovoltaics has much wider application, and organic photovoltaics provides that way. That's why I was very excited while working on this technology during my PhD. Okay, now a little bit about how it works. That just like a normal solar cell, it has a absorber material, which is shown here with a yellow, and it has two contacts, right? Gray color, two different types of contacts. And it can be polymer for organic material. And this cell was proposed much earlier in 90s, you can see, 1993. Alan Heger was the Nobel laureate. He was the pioneer in this technology. Alan Heger, I think he got chemistry Nobel Prize, and he's in UC Santa Barbara. Okay, so now after sunlight get absorbed in a silicon solar cell, you automatically get electrons and holes. But in organic material, generally we get a tightly bound electron and hole pair. It is called exciton. So since it is electron and hole pair, it is charge neutral, right? Because both electrons and holes are together, tightly bound. And that's why it needs a junction to get dissociated. So excitons will diffuse, it will diffuse in the material. The moment it see a junction, it will dissociate. It's like a knife cutting that one. Then in junction, the acceptor material will accept these electrons and donor will remain with only hole. And then because of this inbuilt electric field, because of this two metal, right? So we're using aluminum and ITO. ITO is a transparent contact. So sunlight has to pass through the contact, right? So that's why it has to be transparent. Indium tin oxide. So ITO will take the electron and aluminum will take these holes because there is a work function mismatch between ITO and aluminum. If we use both side aluminum, it will never work because we need a field. And for field, we need a work function difference, two different metal. So that's how they will be transported and that's how the solar cell will work. So that was the concept how solar cell work in general. And for organic solar cell, the junction is very important. It can be PN junction in solar cell in a silicon solar cell, for example. So junction is important to separate electrons and holes into different regions. And the other important thing for this organic solar cell is we need more interface because here we're talking about exciton dissociation, right? The number 3 steps. And to improve this exciton dissociation, we need this junction, right, to as close to as the diffusion length. So exciton diffusion length is in the order of 10 nanometer. That means within this 10 nanometer only those excitons will be useful, right? They can dissociate. Others will not be dissociated. They have a finite lifetime. They may lose out the energy. That's why one innovative concept was called bulk heterojunction was proposed, so that even though exciton length is only 10 nanometer, how to catch more and more exciton in the film. And they did it by randomizing the interface. They just randomize the interface. So no matter where an exciton is created, it will find an interface within its diffusion length. That's the idea. And the same Richard Friend and Alan Heger, they are the pioneers in this field. They proposed this idea, the randomly mixed material. So my research started with this, that, okay, is random optimal or how to optimize this random morphology? So they used to call it the morphology, this random boundary, right? It's called the morphology or the structure of the absorber material. How to optimize this morphology and how to improve the efficiency, because efficiency was around 10% or below 10% when I was doing PhD in 2008 to 13 in that time frame. Okay. So these are the processes, and this is the typical IV curve of a solar cell. So where bulk heterojunction is the new concept, by randomizing the morphology, they have improved the current a lot. And in a solar cell, these are the main 3 parameters, which is called short circuit current, JSC, short circuit current density, And the open circuit voltage, it is the voltage, maximum voltage that you can get. Suppose you open the two terminal of a solar cell and put them under sun. What is the voltage developed between these open terminals? That is the open circuit voltage. Short circuit means you are shorting ITO and aluminum and you are measuring how much current flowing. This is the maximum current. So maximum current, maximum voltage, and there is something called fill factor, which is the charge collection efficiency. So if you multiply these three parameters, you get the output power, right? So JSC times BOC times fill factor is the total power that you get out of the solar cell, and input power depends on the area. Suppose it is 1 meter square area, then you get 1 kilowatt from the sun. So if you know the output power, if you know the input power, you can compute the efficiency. So that's the very basics of a solar cell. And any question here? Anything that I can explain a little further? Yeah, if not, I'll just finish the talk because I have several slides to show. Okay, so now mystery of morphology, right? So that's where I think my contributions were from my PhD studies. So we studied this, we simulated this morphology. We also fabricated later, but initially I started with simulation, that how this blue and red phase separate, right? So how to define a simulation framework so that you can optimize it more systematically. Because when I was doing PhD, most of the time the optimization was done by trial and error method. You mix two material and make this thing work. So we developed a tool. So this is an open source tool. You can use this tool for your classes and all. If you just type this link, you'll find this OPB tool and simulate some of those solar cell as well. The second contribution of my thing was answering this question: is there any motivation to make a very regularized OPB structure? Right? You can make columnar regularized with more processing cost, but is there any motivation? And answer was no. That random is close to optimal. That was the very strong message we concluded in this paper. That bulk heterojunction structure that you get, if you can optimize that structure, that is close to optimal. We don't need any sophisticated regularized structure. And finally, we talked about the reliability. The one reason why OPB is still not popular is because of its reliability. Because silicon solar cell lasts 20 years, right? When you buy our solar cell for roof, we think about 20 years or at least 15 years. For OPB, I think 5 years itself is tough many times. Its efficiency degrades, and there is a fundamental reason. The same morphology, why it is more efficient, right? Random morphology. That morphology keep evolving even under sun, and that's why its lifetime is also quite low. Okay, now a little bit about how it is fabricated. So organic solar cells, as I mentioned, it is an ink-based process. So you mix two material in a solvent, and then you anneal for some time, right? So you anneal at a higher temperature, and during this annealing, this phase separation between donor and acceptor material will take place. So donor is one type of polymer, acceptor can be another type of polymer. So we mix them together. So that's how we make the organic solar cell. Okay, the film or absorber film, and then we deposit metals on them. So this is the different variables are involved, right? Solvent, what donor, what acceptor. So that's why we developed a process model based on the thermodynamics or mixing, free energy of mixing between two material. So this is more like a material simulation. And these are the differential equation we solved to get this exact structure of the morphology. Okay, so that was our approach. And the way it works, okay, when you mix them together, it is 50-50 everywhere, so its free energy is high. But after phase separation, the blue is close to 0 and red is close to 1, so you get a minimum energy, right? So any system always want to go to minimum energy. So that is the free energy concept and the simulation methodology that we used. Okay, so phase separation is the key that dictates the morphology, and that also dictates the efficiency and reliability. So this is the some cartoon and some animation you can see There's a function of time, the morphology changes, and it can be during processing. During processing, temperature is high, so this morphology evolution will be faster. But say as a function of minutes, the morphology will evolve during anneal. Anneal means 150 degrees centigrade, right? And there are a lot of experimental evidences which matches some of those structure, and it also follows certain laws, which is called cluster growth law or Oswald ripening. So these are power law, very well established law for this kind of morphology and our simulation methodology, right? When you simulate, we always try to verify, is our simulation correct or not? So these are the ways we verify that, okay, these are following certain law in the simulation. It also matches some published literature. So that's how we verify our model that, okay, our morphology simulation is correct. So now this is the my first work, and this is the tool that has some part of this work that how to simulate a simple bilayer organic solar cell with some parameters. The GUI based tool, you can change parameters and you can simulate. It is open source. You don't need any, you don't need to pay or anything. It is more like you have to create an account and just play with this tool. I used to use this tool for assignments in my course. So if you want teaching a course on solar cell, you are welcome to use this tool as well. And it looks like it has been used actually all over the world because this tool gives us the statistics where it is being used. Okay, so now let's go to the some of this work that I did. So one is this process optimization, that how long I should anneal. And because if I anneal too little, right, so then the clusters are not well formed. There will be a lot of islands, separate islands. These islands has to be connected because electrons and holes, they need to be transported to the top and bottom contacts. That means islands has to be connected, and that's why the morphology has to be formed properly. So that's why it's very low anneal time is not good, because there are a lot of islands. And if you anneal it long, then also it is not good, because then the cluster is becoming bigger and bigger. It is going towards like a bilayers type of structure, where the exciton diffusion length we talked about in 10 nanometer scale, right? So now if the domain size is more than say 20 nanometer or 30 nanometer, many of those excitons will be lost. They will not find interface. So that's why annealing longer is also not good. So there is optimal anneal time, and our simulated anneal time can really predict the experimentally observed anneal time that we found from the literature. Okay, so this is the early phase annealing, which is sub-percolating morphology, and late phase is the quartz morphology. So that's the reason why we need to be very precise with the anneal time. And yeah. So this was published in that paper that I showed earlier. Okay. Now the same principle, same phase separation principle is also responsible for its degradation, because unlike silicon solar cell, organic solar cell degrades very fast. And the reason is, even under sun, this phase separation goes on, and it will be going on at a smaller scale. It's not in the minutes, maybe in couple of months, right? In a couple of months, domains will be bigger and bigger, ion currents will be low because phase separation. And you can solve this problem analytically, even though it looks very complex, very random structure, like in a more like a your noodles mixed together. But you can simplify it. All you need to find out is what is the total length of the interface. And if we simplify with some analytical model in this applied physics letter paper, we publish this model with this simplification, and it can capture um, the degradation model, that how current degrades with time, right? And as a function of different temperature. So this was our first model, or first model in the literature to predict how long an organic solar cell will last in a normal temperature because of this phase separation. Okay, so now I will give a pause here just to see any questions so far. I'm almost done. I only need maybe 5-10 minutes to finish the talk. Okay, so I'll just go to the last part, which is the efficiency part. So Yeah, so this is the last work that I did during my PhD. It was published in 2015. I was done with this work in 2013. So it took some time, but I'm very proud of this work because it was a very debatable topic. So the reason we mix two material is to separate excitons. So people used to think at the beginning that excitons are the real bottleneck in organic solar cell. That why organic solar cells are low efficiency. I mean, people used to say, or the researchers in this field used to say that exciton dissociation is the real bottleneck. That finding interface or morphology is the key. That's what the usual concept was. But with my say 28, I started working on this field, and with a lot of insights, what I realized it is not just the exciton; it is the charge collection was a real bottleneck, and it is because of insufficient field inside the layers, inside the absorber, which is causing the efficiency loss. And I can explain this little bit better in this cartoon. So you think about direction of light, right? So light comes through ITO. ITO is the transparent contact. Sunlight will come through this contact. But unfortunately, the material choice, right? This electric field is not at all in this contact. Electric field is at the aluminum contact. But light cannot come through this contact, right? So when light comes through this ITO contact, most of the light will be absorbed in this contact. A lot of excitons will be created. A lot of electron hole pairs will be created, but there is no field to separate them. So they will be absorbed and they will be recombining together. Right? That's why I'm putting cross on them. But if an electron hole pair is created along this field region, which is the space charge region, their electrons will be going to the aluminum and hole will be going to the ITO. So that's the idea that electric field is limited only along the aluminum contact. It is not there in the ITO contact. And that is the reason I thought that was my hypothesis. And later we proved this hypothesis with some experiments. Okay. So let me explain this work a little bit more. But before we go there, the efficiency of organic solar cell T2013 was around 10%. But theoretical efficiency that you can compute is much higher. So, and the efficiency improvement take place starting from single layer or planar solar cell, then bulk heterojunction solar cell, then tandem solar cell, where multiple uh, layers will be stitched together. And disadvantage of all this approach is reliability and variability, because there is so much randomness involved that maintaining same efficiency for all cells was near to impossible, right? Variability, and it also caused the reliability because morphology under sun is still evolving. So these are the approach. These are the advantage of bulk heterojunction approach, even though it has improved the efficiency. Okay, and the third loss or third efficiency loss in the structure is this heterojunction loss or delta E, right? Because we are using two materials. So when electron goes from donor to acceptor, they lose energy, right? So that's called bulk heterojunction and junction loss, which will lower your open circuit voltage. And because of all this reason, the theoretical efficiency can be very high using all those materials, but the practically achievable efficiency was very low. Okay, now the first thought I came up with is, can I remove this heterojunction? Can I make a single polymer based solar cell? And usually people will say, oh, no, because at the beginning, right, when in 1993, first organic solar cell was proposed, it was a single polymer based solar cell. And efficiency was very low, minuscule. You can see 0.01%, like much low than what is achieved by bulk heterojunction solar cell. So there was no point going back in the history. But because of, my curiosity, I repeated that experiment. I used the same material. I use only one material, P3HT, which is the only donor. There is no acceptor and two metal. And ideally it should work because two metals will create the field. And if excitons are not the bottleneck, then I should get a very good current. But unfortunately, I did not. I got in microamps, right? This is my result that I fabricated this cell and measured the IV curve under one sun. I got only 10 microamps. And that's why efficiency was very low, 0.1, 0.01%. So there is no surprise in this result, right? Because this is what exactly the Higer and others did in 1990s. Now, I did a little bit different experiment next to understand it a little better. Because of my simulation, I understood that the electric field is mostly in the aluminum contact and light is coming through ITO where there is no field. So can I switch it? So I use a different metal. Now, instead of aluminum, I used gold. And along ITO, I use a very thin interlayer titanium oxide so that I reverse the field. So in this case, just the same absorber material remains same. Just by reversing the contact, the current got 100 times more, right? 200 times more, 2 milliamps. It's the same absorber. Because if exciton was the issue, I would not get that high current just by changing the contact, right? So that clearly proved, and in this paper we presented this result in a much more detail, that excitons are not the issue. It is the electric field issue that are slow or low mobility issue of electrons and holes into the organic material. And we need a higher field to transport them to their respective contact. Okay. And we did a lot of simulation to show how much light is being absorbed near ITO. And this is the energy band diagram that where near ITO there is no field, right? Bands are flat, so electrons and holes will recombine even though they are produced in this first structure. But in the next one, you can see your field direction is changed because of this interlayer titanium oxide and gold metal. And now there is a lot of field where light is being absorbed, and then you can separate them more efficiently. And that's why we get 2 milliamps current. So that really settled the debate between is it charge collection or is it the exciton dissociation is the real bottleneck. And our work conclusively said charge collection is the bottleneck, and that's why improving the charge mobility in the material is the more important than just the exciton dissociation. Okay, so I think I will stop my talk here. I think I'm in time, and I would like to thank all my students at RAM Lab, and also I'd like to thank my funding agencies which fund some of this research and the recent graduates from our lab. Okay, so thank you everyone for your listening, and if you have questions, you can always email me. You can ask me now, whatever time is left. So thank you very much.
Thank you, sir. Participants, any questions, please?
Can you go back to the last slide? You were telling that there is a problem with the field. Comparing this one, that is with aluminum and the gold. In the sense, what is the level of the voltage maintaining? Do you mean by field the volt per particular dimension, or you mean different?
Yes, so yeah, so this is a good question. Sorry, I didn't mention that we're talking about short circuit condition, right? So we are not applying any voltage. So both aluminum and ITO will be shorted. So now in solar cell, we get short circuit current. So even though both the terminals are shorted, there is a work function difference between aluminum and ITO, and that will cause the internal field. So in solar cell, in PN junction, we get electric field free of cost, right? We don't need to apply voltage from outside because of material mismatch, right? We get field. Think about a PN junction. So it's a diode, right? So PN junction diode, you short both the terminal, but inside the junction, in the PN junction region, in the depletion region, you get a field because of charge, right? Fixed charge. So similarly, I'm talking about this field here, that even though you have not applied any voltage externally, both aluminum and ITO are shorted, still internally there is a field because of work function difference.
Will that field will be able to drive the charges to both sides?
Yes, and that's why we get short circuit current, because in a solar cell, during short circuit, we get the maximum current. So when you apply field actually from outside, right? When you say at open circuit voltage, there is no current. So at open circuit voltage, the two terminals are open, right? So there is a huge voltage you apply basically, or you is created. So that time the internal field will be low. And that's why a lot of recombination happens during open circuit. That's why whatever sunlight generates are lost in the recombination.
So what is the contribution of actual the sunlight, how the energy transfer from the light to the
Yes.
cell?
So I understood. So in short circuit, we don't get any power. You get only current because for power we need current times voltage, right? Both we need. So
Yes.
if I go back to my maybe this slide, at the beginning slide. But this is really good question because, and I like to explain that because these are subtle questions and uh, I find it interesting. So if you look at the short circuit point, right, you get the maximum current, but there is no power. Because for power, I need voltage, right? Because it is 0 volt. 0 volt because the two terminals are shorted, but current is maximum. So all this sunlight that is being absorbed, they're creating electron and hole. All the electrons are coming out because of internal field, but they're not doing any work. So their energy is lost in the I mean, when electron moves from one contact, goes to the another contact, so there the energy will be lost. So you're not getting any power. And in the open circuit voltage, you get the maximum voltage out of the solar cell. But again, no power because there is no current. So your maximum power point, that's why it's so important in solar cell to operate it in a maximum power point where you get this green point, where you get current as well as voltage. When you get current as well as voltage, that's where you are getting some power. So to answer your question, where the sunlight power is goes. So in open circuit voltage, everyone recombines. So all the powers is lost inside the material. Right? Sunlight creates electron hole pair and they recombine, and that's how the powers is lost because nothing comes out. In short circuit current, yes, you can say a lot of electrons comes out, but they're not doing any work because they're shorted. And electrons from ITO will come and recombine with aluminum at the other side, right? And that's where the energy will be lost, the recombination loss. It is only at the maximum power point where recombination loss will be minimum and maximum energy transfer will take place to a load. I hope I make some sense.
Yeah, understood. But the thing is actually, if you want to have that is connect a load
Yes,
to this, and we
yes,
can make it to the operating point of the maximum
absolutely,
power point.
absolutely.
Uh,
So
and
the load, yeah,
uh,
yes.
since you are telling about the organic type
Hmm.
of a thing,
Hmm.
uh, and if can we make a kind of a cell? Have you tried as a cell? How what will be the sense number of cells per the dimension of square or rectangle, whatever you have?
Hmm. So yeah,
Is
I
there
think
any working there?
yeah. So my cell structure looks like this. Oops, sorry. So this is how I mean exactly. This is really made by me. So that long time ago. So mix this ink. This is the cell dimension. It's like a coin, small, say 1 rupee coin size, and three lines are the three cell basically. So so three cell in one processing. This is in lab, right? In a university setting, we did. But in a commercially, they'll do much better, much more cells in a large area things. But this is for lab, and this was a three cell in one setting. Yeah.
So, what is actual the power you derived for a standard lighting of conditions?
Yeah, it is much low, much low. The efficiency that I made, my made solar cell was around 1 or 2%. And based on area, you can find out what is the total power it will be giving.
So, it
Yeah,
is
yeah.
not comparable to the commercial
No,
solar
no, no,
cell
no,
voltage.
no, no. So my work was mostly answering some of those fundamental questions, that is exciton was the bottleneck or is charge transport is the bottleneck, so that research can be done to improve the charge collection efficiency and all. And I think after that paper, right, that I showed in PNS, so this paper was very, sorry, this one, PNS work, that settled the debate, because this was very clear that excitons are not the bottleneck. It is the charge collection is the real bottleneck, and electric field management inside the device is the real issue.
Understood. Thank you.
Mhm. But thank you for asking this question. This is insightful. Yeah.
Thank you, sir.
Mhm.
Good evening, everyone. On behalf of the entire team and participants of the FDP, I, Anita Sampathkumar, Assistant Professor of Triple E Department, extend my heartful gratitude to our esteemed resource person, Dr. Biswajit Rai, for engaging insightful and thoughtful provoking section. We truly appreciate the time, effort, and preparation you have put into the delivering this session, making it not only informative but also interactive and impactful. We hope to have much such opportunities to learn from you in future. Now I take this opportunity to thank Dr. M. Chakrapani sir for introducing such a renowned person to us and for contributing to the success of this and for contributing to the success of this event. Thank you, sir, for joining us with us in the midst of your busy schedule. Once again, thank you for being with us today and for making the session a memorable and enriching experience. Thank you, sir.
Yeah, thank you everyone for listening. I know I dragged it a little bit longer, but you can always ask me questions if you have. You can email me. My email IDs I can share, and also my slides will be there. You can uh, find my email
For the
there.
sake of participants, will you be able to share your
Yes,
email ID on the chat, sir?
yes, that's a good idea. Yes, this is my email ID. You can always email me in this, and I'll be happy to share more information or answer if you have any questions or any of those. And yeah, thank you very much, and have a nice evening, and have a good dinner. Yeah, I'm sorry I'm sitting in between your dinner and you. Yeah, bye.
Thank you, sir. Thank you, sir.